Alright guys, so I'm going to give you the answer key for that. I promised you that last time. Yeah, the quiz corrections due on the day of the test. And the quiz of the previous test, the corrections of the previous test are due on the day of the test.
So, the total
Is everybody? Maybe. All right. So I tried. Oh, sorry. One more. That's one more back there. I tried to write out a little bit more explanation of what's going on. And this is my suggestion as to how to represent this on a quiz or on your homework. Definitely box the answer in, because there's going to be a lot of like marginal work going on your problems. Don't make it a Where's Waldo problem for me to find the answer. So box that answer off. 4B we're going to talk about a little bit. I put the algebra that you need on there. And 4B actually represents one of the coolest little things ever. So let me show you. So on 4B, the first step, let's actually go through 4B, and I want to show you how I use that formula in a different format to help me do this. 4B asks me the 35th percentile. So that means that there's 35% below it. So if you want to double check, when you look up 0.35, the closest I could get in the chart was 0.3483. Because the other option was 0.3520. This one's 17 away, 3520 is 20 away, so that's the closest. So many guys, it would be cool. So it's officially negative 0.39. But it's almost right in the middle, so some of you, if you want to, you can cut the difference like they did with the 1.645, where they split the difference right in the middle. So it's up to you. This is fine, though, to do this. So is everybody cool with me so far? We did a problem like that earlier on this handout. What z-score has this area below it, so you look it up in the chart. The closest I get, 3483, that's negative 0.39. Now the new thing is, a z-score is not good enough here. I want the time that would put somebody in that percentile. So I know the answer. What does that z-score tell me? What's the z-score tell me?
Below the mean. Below the mean.
I like it. So how many standard deviations from the mean to the data point, right? So you could probably do this without a formula at all. I'm this many standard deviations away from the mean. So if I started at the mean here was 8.64. Do I want to go up or down?
Down.
Down this many standard deviations. And how much is the standard deviation? In this problem? 2.27. And then you just do that. That's just applying the definition of z-score. Start the mean and go this many steps. Holy shit, you could read that in English. Take the mean, go down this many steps. That's crazy. Now here's where the algebra is going to back up what we think we should do mathematically. How do I solve this for x? Pretty much stepped it out for you up there, but because if I know x mu sigma, then I can get a z-score. That's what this formula is good for. But if I know z, mu and sigma, I want an equation that has x by itself already, so I don't have to solve every damn time I do a problem, right? That's part of the whole reason you guys learn how to manipulate variables in algebra, is so that you can make better equations for yourself in future classes. And here it is, a future class. So how do I solve this for x? What's the worst part of that equation?
You multiply
The fact that it's got a division in it, a fraction, right? So of course, to kill that fraction, I just
you multiply.
multiply by sigma on both sides. So I get z sigma equals x minus mu, because those go away.
And then you add the mu.
And then you add the mu. So you get x equals, so add the mu plus z sigma. Isn't that exactly what we did over here? I know it's got a plus sign in it, but it's cool because the z-score in this case was negative, so you do end up going down. So look what this is. You are not allowed to write notes on your formula sheet, right? Some of you know that all too well. But look what this is. This formula is a note. What does a z-score tell you? It tells you the number of standard deviations from the mean to the data point. Holy shit. You guys semi with me? Some of you not at all. Okay, that's fine. I'm trying to show you. It's really nice. You know I'm going to ask you every single test, what does a z-score tell you? And what I'm telling you right now is you're allowed to have formulas, and this formula is double duty. It acts also as a note. That's crazy. And it's really cool. You just got to start to realize a lot of formulas in classes that relate directly to real life. Right? Some of math, I will agree with you, is abstract and it doesn't relate directly. This relates directly. You probably can say it in English then. And we can't. Cool. All right. So that's enough on that, guys. So this guy can sit on your formula sheet now. And of course, on the review day, we'll write that down as being officially something you can put on your formula sheet. Cool. So you use this. Let me try this here. On number 4A, every single one of those problems did this. They gave us an x score, right? At least one x. We converted it to a z, and then we looked up the probability. You with me? So of course here we looked up, we used the formula here, and here we used the chart. You guys with me? Now look at the problem here. Look at this problem. This is exactly backwards. They gave me a percent. I used the chart to look up the z-score. And then I used the formula written in a nicer way to work back to see what the x-score is. So that's a classic z-score problem. They either give you a raw score, you convert it to a z-score, you look it up, and you get the percentage. Or they give you a percentage, you look up the z-score, and then you convert that back to a raw score, a time, or a number of people, or whatever it is you got in your problem. Cool. I love the way most of you do not react in any way. You're like just shell shocked. I love it. I'm hoping some of this is making a little bit of sense. I'm trying to give you some overarching ways to look at these problems. Are there any specific questions out of the homework? Anybody in the chapter 6 homework? Yeah.
Oh, well, I have one about 5.
Okay. I will allow.
Number 4 on 5.4. Page 2 something. 226.
So, a statistics class consists of 10 females and 30 males. Each day, 12 of the students are randomly selected without replacement, and the number of females is counted. Using the methods of the section, blah, blah, blah. So, behind the scenes, and in fact, very prevalent if you look up the definition of what a binomial probability is. There's a key thing that this does not follow. So binomial probability has to have a P and a Q. They have to add to 1. So there must be 2 outcomes. But really what's key, what really lets me, remember when we did 5 left-handers? Remember those days back? when things seem hard, and now you're like, nah, that wasn't hard, here's the hard. Remember when we did this?
Right.
First one's left-handed, times the second one is not, remember that?
Yeah.
Why am I allowed to keep repeating that Q? Doesn't that mean that Q, that probability is not changing every step?
Right.
Wouldn't it so desperately suck if it did change every step? Then you'd have Q1, Q2, Q3, Q4, and I couldn't write it as PQ to the fourth, because they're not all the same. So what is it about this problem that says the probabilities every step I take won't be the same, that they will change
So each day, there's no, it's not the same number?
without replacement?
Yeah.
If they only did this with replacement, it would be okay, but they did it without replacement, so the probabilities change. I couldn't write Q, 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 because now it's sort of like the king and then another king. Doesn't the second guy change if I do it without replacement, and then become 3/51? So I can't say that they're all the same if it's without replacement. So this section won't work worth anything. So the last thing you need here is independent events. If they're dependent, then these will change every step. There's no way to consolidate it. There's no way to make it p to the x, q to the n minus x, because they're not a bunch of p's and q's. They're a bunch of p1, 2, 3, 4, 5, 6, q1, q2, q3. Screw that. Let's not go there. Again, I love it. It's not like, what? It's not like, yeah. It's like, I'll not give them anything to work with. Okay. I do what I can. Who asked the question?
Me.
Does that make sense?
Yeah. That's what I put, basically, so.
I definitely have at least one person. Okay. Anybody else? Any questions from 5 or 6? Yeah.
Chapter 6, number, 6.2, number 5.
Oh, good. Very good. This is one of those moments that I kind of purposely build in, that if I don't get the question, then I know probably nobody's gotten into this stuff yet. Because we didn't talk about this. This is talked about in the section, but I didn't talk about it. And that would be a uniform probability distribution. And all the uniform means is that every probability is the same. So for example, if I have rolling a die, to draw that, if I roll a die, what would that look like? Is a histogram? 1, 2, 3, 4, 5, 6, and they would all have the same probability. They would each have a probability of 1/6. You guys with me?
Yeah.
And the really cool thing is, well, John is a little bit freaky, but that's too bad. This is a 6 wide times 1/6 tall is a total area of 1. And that's what probability distributions have to have. They have to have an area of 1. So this is like the easiest probability distribution in the world, unless you're uncomfortable with the idea in the first place, which most of us are when we start chapter 6. So here's how this works. In this example, they give me, what was it, number 5?
Yeah.
So on these examples, they say 123 to 125 volts. It's a uniform distribution.
That's number 7.
Well, it's number 5, 6, 7, 8, all those. So assume that a voltage level between 123 and 125 is randomly selected.
Oh, I see.
Oh. And it says refer to figure 6.2. So they kind of set this up for you already, I think. Here it is. Yeah, and it kind of makes sense. How wide is this? 2. So how tall should it be? 1/2, because the area is supposed to be 1. Okay. So all I have to do now, this is a really nice problem for what I was trying to do with the histogram picture and the idea of area. If they ask me any question for a probability, I just find the area of that question and I'm done. The area is the probability when you draw it out. That's kind of nice, especially when you have an easy-ass picture like a rectangle. So when they ask me, for example, greater than 124, well, what's the area of this block here?
1.
1 times
1 times half.
times a half, so that probability of greater than 124 is 0.5. Yeah.
And the half you just got from the diagram, there wasn't anything problem that said that?
Yeah, they didn't even really have to do that for you, because you know it's 2 wide. The width is 2, so you know the height has to be 1/2.
Oh.
What if it's like 123.2?
Cool. So how do you mean? Like another example
Yeah,
where
like
your
number
probability?
7 is like between 123.2 and 124.
I like it. 123.2 up to, what is it? 124.7? Let me take this off of here. So we're at 123.2 is like right there. 124.7. Well, how wide is this?
0.9.
Careful.
0.9.
Yeah, it's 0.9 wide, right? Isn't that the difference between those two? Isn't that how wide? Oh, why did I put 0.8? My fault. So it's 1.5. So isn't that 1.5 wide? Make sure, is everybody with me? Because it's from 123.2 to 124.7. How far apart are those? 1.5. That's the width. What's the height? Half. So it'll be 1.5 times 1/2. Yeah, so 1/2 of 3/2 is 3/4. So it'll be 0.75, or 75% chance. Okay. That's not too bad, right? I like that. So I like the idea of if you put that rectangle up somewhere and you had people just throw darts at it. If the dart lands in the rectangle, what's the probability it's going to be in this area here? 75% chance, because there's a 75% area there, right? Just randomly throwing them up there. Don't count the ones that land out there. But the ones that land in there, there's a 75% chance to be in there. So why is the bullseye so damn small? Because you get the most points for it, because it's so hard to get it in there. Depending on which game you're playing. Yeah.
So for like the first one, for greater than 124, is it like assumed that it's approximately 0.5? Because technically wouldn't it be, like there would be.
Now here's the thing that blow your mind. What's the probability of exactly 124 volts? So really think about that question from the context of this. What's the area of a line? Yeah, it's not quite 0. It's actually, let me make sure everybody's with me here. Now think about this. If I think of a number between 0 and 1, and I mean any number between 0 and 1, so 0.79244444567, that's possible. What's the probability you're going to pick my number? It's essentially 0. It's not quite 0. Right? So I like this visually. The probability of any single output is essentially 0, because what's the area of that thing? 0. What's the width of a line? Who remembers their geometry? 0, exactly. But here's the really cool thing. We all know the biggest number. It's not really the biggest number because you can't get there. Infinity. Well, here's the smallest positive number. Now think about that. Let me say it again. Smallest positive number. I don't mean whole number. Don't say 1.
1 over many.
Yeah, 0, 0, 0, 0, 0, 0, 0, 0. In the infinite place, there's a 1. Okay? You can never get there. That's actually called iota. And as I'm talking, I forgot the symbol all of a sudden. I can't remember the symbol. The symbol's just gone away. Because I always think iota. I don't really think about the symbol. Oh, but have you ever heard that word iota? Some of you might have, like you have a, what's the chances there's an iota chance, or I can't remember how is it normally said. Some of you guys might have heard this word before. And a lot of you guys don't care at all about what I'm talking about. I understand. But I love this idea that it's only regions that have probabilities. Any specific number is so unlikely it's basically 0. And that's what the area is saying. What's the area of a line? 0. But truly it's just above 0. Otherwise, how can you add up a bunch of lines and actually get an area if they're all 0? So there must be something just barely above 0. That's way too deep for that problem, and I just decided to go there. So these problems are nowhere near as difficult as that. find the width, multiply by the height, you're done. Uniform distributions look like they should be easy, and they are. This distribution, not easy. Is that a nice shape for area?
No.
Hell no. So I need calculus people to help us make that chart that we use. Cool. Because calculus is good for finding areas of any shape. All right, so anything else I can go way too far with? Any other questions? Okay. Now you're all scared to ask me, I understand. What kind of weird stuff is he going to talk about? So today, what I want to do, and I do not mean to ever make you scared about something, but I do want to make the point that we're getting into an area that most students have a lot of trouble conceptually. The nuts and bolts work is stupid easy. The concept is stupid hard. So of course I'm going to go through the whole concept and I'm going to lose a few of you guys. Then I want you to come back with me when I talk about what a problem is going to look like, because then it's going to be really pretty simple. So you're all like, well, skip the why, Jeff. No, you can't. You know me. So what I want to start with is just a little review. If I have a normal distribution, let's say the mean is 103.7, and the standard deviation is 12.91. Find the probability that x is more than 120.1, and find the probability that x is between, yes, Jeff, I don't know, between 85 and 150. No. There's UFO going over here. Just make sure everybody on the right track. You will have to use what? What will you have to use eventually? Z-score chart. Love it. Alright, so on my drawing for part A, what goes right in the middle?
The mean.
Yeah, 103.7. Where's 120.1? Up here. And I want the probability greater, so of course I shade up 11, or to the right. So I want to convert these to z-scores, so then I can use that z-score chart. So to get the z-score, x minus the mean over the standard deviation. So my data point is 120.1. The mean is 103.7. Standard deviation was 12.91. What do you guys get for the z-score there? Oh, I get it. Difference of opinion on it. Yeah, I get 1.27. So make sure when you put it in the calculator, put the parentheses around there.
Oh, that. Famous.
Oh, yeah. So 1.27, that's my z-score. So I know I'm up from the mean a little more than one step, which we actually knew from the beginning. One step is just under 13. 120 is definitely more than 13 above 103. So I'm a little more than a step up. So when I look at the z-score chart, it knows as I move how much more area there is below it. So when I get to the point of 1.27 up, when you look that up, how much area is below that? You look at 1.27.
It's 0.8980.
Yeah, 1.27, 8980, I love it. I know I'm not done yet, but is everybody able to get that number? Don't say anything, I'll assume that's a yes. All right, and then of course, how do I get my actual answer? Yeah, 1 minus that for the rest, because that's that side, I want that side. 1 minus 0.8980 is 0.1020. Cool, how we doing? Some of you guys might like the shortcut I told you. If you look up negative 127, you actually get the answer directly. It doesn't save enough time to really worry about it if you don't quite understand it, so don't worry about it. And what about part B? So part B I just have two parts, 85 and 150. So I want this area in between there. So I've got to find a z-score for 85, and I have to find a z-score for 150. So for 85, it'll be 85 minus the means, divided by 12.91. What do you guys get for that?
Negative 1.39.
Neat. All right, let's see. So 85. I get negative 1. I don't think I heard anybody say this. Negative 1.45.
That's what I.
Cool. I get negative 1.4484. Blah blah blah.
Oh, I did.
That's right. And then what about for 150? $3.59? Yeah. 3.59. So I kind of did that on purpose to you, because when you look it up, well, let's start here. When I look up negative 145, what area do I get below there? 0.0735. So you guys got? All right, I'm a trusting fool, so yes. And then what about 3.59? What's freaky about that? Yeah, and the thing I disagree with that chart is it's not always 0.999 once you get past 3.5. If you were at 8, if you had a z-score of 8, screw it, that's basically 100% below. It's not 0.9999, it's picking up more and more area as you go further and further out. But if you want to go by the book, you can always make that 0.9999. But what I say is, if it's off the chart, it's essentially 100% there. It's close enough to call it about 100%. So how do I get my area in this case? So 0.9264, yay.
See, for that, I got 0.9998, something like 0.9999, yeah. Or-
Well, it's definitely above 3.5. So be careful, you look at 3.49, 3.59.
Oh, I
Yeah,
see.
Cool. Alright, so is everybody semi-comfortable with that? I mean, if you haven't gotten to the homework, you're not fully comfortable with it, but once you get some practice, even if you don't really comfortable with it, it's very straightforward. It's very recipe-ish, right? Which is not a bad thing at all. Because you have to be pretty comfortable with this, because the next two main ideas we're talking about are tweaks to this in certain situations. Oh yeah, Jeff. So, let me see, I don't have the most time, so let me if you were to go out right now, and you could just go anywhere in the United States you wanted to, just, you're there, and you randomly select a dude, and if that dude was 6'5", would you be freaked out? Would that be unusual? No, right? It's not unusual. That we could do the work if you want to, because we know the mean and the standard deviation, we can calculate the probability and all that crap. But that wouldn't really freak us out, would it? Now, being able to transport yourself anywhere in the United States, that's freaky, but let's just assume that's all known. If I just select one man from the United States at random, and he's 6'5", I wouldn't say that was excessively freaky, right? You guys semi with me? If you were to go out and randomly select a group of 50 men, with me, and their average height was 6'5", would that freak you out?
Yes.
Good. So that must mean something fundamentally different about the pictures in those two cases. The pictures we've looked at so far, this picture, every picture we looked at so far is all about individuals. In statistics, what do we normally work with?
Groups.
Samples, groups. I love it. So I'm not saying the work we've done so far is all crap. I'm saying it's necessary, but what happens more often is the freakier case. So here I have, I think the average height for men, why did you just go out? It was 69 inches and only 5'9". So if I found one dude that was 6'5" tall, that would not freak me out. It's not very unlikely. Right? So if you're telling me that if I get a group of 50 men that that it would be freaky, then the picture can't be the same. Do we all agree there? If the picture was the same, the probability was the same, why would you freak out? So you're telling me the probability must be much smaller, so there must be less stuff out here. There must be more stuff in the middle. Because if you pick a group of 50 men, I would put money on the mean being close to 69 inches tall. Right? Because if I pick 50 men randomly, their mean height should be close to the real mean. But if I pick one dude at random, I'm not putting any money down at all. Shit, that dude could be anything. He's going to be less than 8 feet tall. I'll put money on that, but it's probably not much of a return on that. Right? All right, so here's the idea. I'm going to go back to an example that I really like from earlier. Remember the ages in Florida? So here's where we're going to take this up a notch. So this is obviously not normal at all, right? Okay, good. If I start taking, so this is individuals. Individuals. So I asked, how old are you? I'm 2. How old are you? Maybe 7, right? We both have the same voice. Let's just get over there. So that's samples of size 1, if you want to get all technical. This is just looking at individuals, and that's all the work we've done so far. Now we're going to say, well, what if I take a sample of size 20? Can anybody tell me what's the most likely thing that will happen if I take a random sample of 20 people from this group? Is it likely that I'm going to get 20 there? No. What's most likely?
10.
Or in the middle.
Yeah. I like the way you said it. It's not exactly that, but but most likely would be some from here, some from there. Right? What's most likely is that. And where's the average of those groups going to be? Right in the real average, isn't it? So the new picture is going to look, it's going to have around the mean, it's going to have a peak, and it's going to be pretty relatively tall, because what you just told me was that's most likely. What's next most likely? Would be a lot of people from here, and then just like one or two from there, and so I have it like, what's actually going to end up happening is I have a little peak here, then a peak there, and then a peak here. Can you guys understand that? Most likely, and then the other two possibilities are that. It's a little bit more pronounced than it would really be, but of course it is. Let me explain. So let me ask you this. Which picture has a larger standard deviation?
What was the first one?
Yes, because more of that data points in the first one is further away from the average. Here, what really happens is it rushes to the mean. It tends towards the average. As I pick larger and larger samples, their averages will tend towards the average. Yeah.
So what is the second picture, what is that? Is that the probability of choosing 20 people?
So I'm plotting 20 people. So I'll pick 20 people. I say, calculate your average age. What's your average age? 2. Good job, little 2-year-olds. And then I'll plot that. So here I'm plotting individual people. What's your age? Bam. What's your age? Bam. Here I'm saying you 20 people. What's your average age? Bam. You 20 people. What's your average age? Bam. Yeah.
So even there, if like that's representing 0 through 30 and that's like 60 through 80, you might not have a single 45-year-old person, but that would be the average age for the second
Exactly.
one.
That would be
Because
the
there's a
average
single
of the
person.
samples I'm picking, the
Right.
most likely thing, because the most likely thing is a mixture.
Right.
Then I actually do get my average age.
Even if not a single person.
Even
is
if not a
that
single
age.
person
Yeah.
is that age.
I'm just a little, I just wanna clarify, so the second picture is like, if you picked a series of groups of 20, and you collected their average age, the figure would look like that. Okay.
So this is like every single possible group of 20 has been plotted, and most of them will be right there, right? That's the idea. And the fact is, are these two means different?
No.
I know I've used the same symbol, but the actual symbol for this case would be this. Now what the hell is that? What am I doing to get that point? 20 people, and I ask them, what's your average age? So what symbol would I use for those 20 people that I selected and their average age? What symbol would I use? X bar. So what's this? Is the average of all of those averages. So that's why it's the average, oh shit, of the averages. No. So let me give you something that, if you look at it, and please try to look at it. We'll talk about this next time, obviously. It's a little hard to understand fully on your own, but you can certainly kind of get the idea what's going on. So I want you to look at this. This is going to get you into 6.4 and 6.5. And let me say this. This will help you with the homework you need to do in 6.4. And that's like the most colorful handout I've ever done. Very colorful.
Almost. I know school was good at wood coloring these things.
Good point. This is one actually.
Oh. This is
Hopefully-
like, my handouts are always been black and white for the last 3 years. You're right, I don't.
So, hey, the 3 guys in the end, I left a few in the printer in there just so I could make it to class semi on time, so let me run and get you guys. You got a minute? Come by my office? Good. Okay. All right, guys.